Okay, so we're talking about just describing motion in a circle. And we talked about the fact that you can do something called angular displacement. So that's talking about how you're moving in terms of angle. Of course, when you're moving on a circle, every motion you do can be talked about in terms of angle as well as just distance. So angular displacement is a vector. It can only point one way or the other way. So in many ways, it's like one-dimensional motion. Positive is counterclockwise, negative is clockwise. We have to make sure to measure in radians because if we ever want to pop over from the angular world back to the linear world, it's going to be crucial. So, for instance, this formula right here, that some of you may have seen in math classes called the arc length formula, if you supply how much angle you've covered and how far out from the circle you've done that, so in other words, the radius of your circle, it will supply you the physical amount of distance in meters that you've covered. Okay? So there's a relationship between the distance, s, the radius, r, and angle you've covered, delta theta. I guess I should mention first off that though it's not commonly written here, when you're mixing angular and linear stuff, the old stuff and the new stuff, their ways of dealing with sine are completely different from each other. So if you want to make a comparison, don't worry about the signs. Plus and minus has very different meaning in the two worlds. So if you're trying to change from one world to the other, the minus signs can't come along. So it's almost never written like this, but you should be aware there's kind of these phantom absolute value signs here. So we wouldn't put in a negative angular displacement here, even if we were going clockwise, because that would translate to a negative distance, and that doesn't mean anything. There's no such thing as negative distance, right? So this is our relationship. We can always go back and forth between how much angle we've covered and how much distance we've traveled if we know the radius. Okay? Let me remind you again that s is a distance, is measured in meters, and r is also a distance, that's measured in meters. So the whole idea of radians, it's a fake unit. It doesn't really exist. Okay? A radian is a way of talking about ratios. Okay? So it's a way of talking about angle in terms of ratios of s to r. So distance you covered to the radius of the circle. So the definition of 1 radian is when you've covered 1 meter of distance to 1 meter of radius. In other words, you've covered an equal amount of distance along the circle as you are from the center. If you want to see another picture, a way of visualizing what a rad is, this is what a rad is. I take a ruler, I draw a length. It's a bendy ruler, so I can also bend it like this. That length is the same as this length. And that does define an angle. Okay? When this is 1 meter and this is 1 meter, this is 1 rad. Okay? That's what a rad is. Okay? And it turns out that you can fit just over 6 of those and make a complete circle. In fact, 6.28, which we normally call 2 pi. Okay? So that's what a rad is. Okay? So 1 circle is 2 pi radians, so a little bit more than 6 of those little wedges. So 1 rad is a pizza slice where the distance along the crust is the same as the distance to the point. Okay? So let me now start to talk about why we would want to talk about your motion along a circle in terms of angle in the first place. Why not just use s? So let's talk about that. So let's imagine that this thing right here is a spinning carousel. Okay? So a carousel is a rigid platform, right? With a bunch of horses that are basically attached to it, right? So let's take a look at a rider on the edge here. That's going to cover that distance, s. And maybe a rider in somewhere toward the middle. They're going to cover that distance. I'll call that s2. Now let me ask you this. Do they both cover the same distance, s? No. Do they both have the same radius, r? The distance that this guy is from the center of the circle is much smaller, right? They don't have the same s. They don't have the same r. How about the angle that they've covered? That's the same. That's why we use angle, because when we have an object that's rotating, different parts cover different distances because they're different radii, but the one common theme is that if this is a rigid object that is not falling apart, then you can be guaranteed that everybody does the same thing in terms of angle. Not in terms of distance, meters, but in terms of angle. Okay? So in fact, in this equation, everybody has the same delta theta, but if you're at a larger r value, you're going to cover a larger distance. Okay? In fact, if you are making a circle that's twice as big as somebody else, then you are going to travel twice as far in the same time. Does that make sense? So the whole reason why we're moving to angular kinematics and talking about everything in terms of angle is because that's what everybody has in common on a rotating object. Does that make sense? Okay, so we can write here that, I guess I'll call this S1. So R2 is smaller than R1. So S2 is smaller than S1, sorry. But the delta thetas are equal. So hopefully that motivates you why we have a strong reason to start talking in terms of angle. Okay? So the carousel analogy is hopefully apt. Okay? We have a rotating object with different radii available on the same object, right? It can be further out on this circle or closer. So then we bring in angular velocity. That is the Greek letter omega. It looks like a rounded off W. If you already write your W's without nice crisp corners, then you might already write it like that, but I would try to make sure that your omegas are distinct from W's. Okay? So angular velocity is exactly what you think it is. We define it exactly the same way. It's just your average angular velocity, you just take your angular displacement over time. That's just a bizarro looking version of what we did in homework number 1. Look at the comparison. It's exact. If you want average velocity, take displacement over time, take that sentence I said, throw an angular in a few places, and you have the new stuff. Okay? Before, velocity was measured in meters per second. Now it's going to be measured in radians per second. So let's take a look. Well, same deal. If the displacement was positive, it meant that the angular or the velocity on average was positive. That was on your homework 1. You can't get displaced to the right if you don't, on average, go there, right? You can certainly, doesn't mean you have to travel to the right all the time, but you have to average out going to the right if you're going to end up to the right. And likewise, if the displacement was negative on average, you have to have a velocity that's negative. You can't end up to the left if you don't on average go to the left. Same deal here. The sign is given from the displacement straight to the average velocity. If you go counterclockwise, on average, you have to go that direction. Remember, you don't get a credit for coming back around. If you go around one full circle, we call that 2 pi, not 0. So the only way you can wind up counterclockwise from where you started is if you, on average, go that way. And the only way you can end up clockwise from where you started is by, on average, going that way. Same deal. If you understand homework 1, this is the same deal. Let's take a look at something that's spinning at a constant rate. So an example like a carousel. So we have a carousel that's spinning. We're going to neglect where the riders get on and then it gets back up to speed, and we're going to neglect the part where the ride's over and it slows back down so everybody can get off, right? So it's just spinning at a constant rate, okay? So let's compare these two. We don't need to put average here because, of course, it's going to be spinning at a constant rate. And here's where we can think of this as kind of like a little orbit, right? So if you're making a circle, the distance around is 2 pi r, and the time it takes for you to complete that, we call that a special letter. We call it a capital T or a period. So let's once again compare our two riders. This will be rider number 1 again. This will be rider number 2, right? So we have a typical carousel. Rider number 1 is on the edge. Rider number 2 is toward the middle. Now they're both going to complete a full circle in the same time, right? So this is the same for both. But the r is not the same, right? So if r, which r is bigger again? R1, the person on the edge. So if R1 is bigger than R2, what does that mean about the speed? Faster. You get a bigger thrill riding on the edge of the carousel, right? You're going faster through the air. You're going to feel the wind more. So you'll find that the older kids, right, are going to ride on the edge. You want to try to grab a seat on one of the edge horses, right? It probably means that you're ready to graduate towards something more exciting, right? A roller coaster or something, okay? The little kids ride more toward the middle, right? So that they can actually move slower, less meters per second, okay? Does that make sense? They're all on the exact same rotating body. They all complete one period at this, the one circle in the same time. But if you are closer in, you're going to go slower. But there's something to be said. There's something that we want to say is similar about the two. Well, that's where we come into angular velocity. So if we talk about angle covered per time, they both cover an angle of 2 pi in one period. That's the same for both of them. So we're taking out the one ingredient, radius, which is the thing that was different. So they're going to have the same common angular speed. They don't share the same linear speed, v, meters per second. They share the same angular speed, radians per second. They both cover the same angle in the same time. That's what's the same about the two. And it's, by the way, the same for every single rider. It can be said to be a property of the entire carousel is what is the angle it covers per time. When I say constant rate, what I really mean, actually, is its constant angular speed. There is no such thing as a common v for all different parts of the carousel. Points on the edge are moving more meters per second. Points toward the middle are moving less meters per second. There is no v that's true for the entire thing. There is a common omega that is common for the entire object. Okay? So you will find that for many rotating things, when you want to say how fast it's spinning, you are using an angular speed, not a linear speed. One example might be a record, a vinyl record. Does anyone play any vinyl records? It's making a big comeback these days. It's all vintage and cool again. Okay? There's a button on your record player where you can set how fast it rotates. It depends on what kind of record you have. There are records that are 33 RPM. That is a non-SI unit for angular speed. RPM means revolutions per minute. So it's per minute instead of per second. Well, that's not a big deal. It's per time. But the thing on top is not a distance. A revolution is another way of talking about angle, right? One revolution is 360 degrees or 2 pi radians, right? This can be converted using your unit conversion. It's about 3.5 radians per second, okay? So anytime that there's a spinning object where different parts of it are making different radii of circles, it makes sense to talk about it in terms of angular speed because that is the common thing that you can say is true about the whole thing. Again, different parts have different V's. Points further out have more meters per second. Points closer in have less meters per second, right? But everybody covers the same angle in the same time, okay? And by the way, if you look at these two formulas, you'll notice the only difference is that this is missing R. We see that one ingredient that's different. In fact, this is a general relationship, not that I've proven it terribly rigorously, but if you multiply the R back into omega, you'll get V. So you can certainly see it's true here. It's true even when, in more complicated cases, they can always be related like this. And once again, you have your ghost absolute value signs. They are almost never included, but it is understood that the plus and minus in both of those worlds are so different that you can't have signs coming along with the ride, okay? So with this in mind, I want to go ahead and start making kind of an organized chart of all my stuff. I'm building up enough equations here that I want to kind of organize it. This is basically going to be similar to the summary sheet that I posted for you. So you may not, it's up to you whether or not you want to copy it down, but I will also provide it separately. So over here I'm going to put linear to angular conversions. So anytime you want to convert between the two worlds, between angle and distance, you can use these equations. S equals R delta theta is the first one. V equals R omega, that's the next one. And just so I don't have to put the ghost absolute value signs, let me remind you, sizes only, okay? So don't let any negative signs sully these equations. S is in meters. V is in meters per second. That's on the linear side. And over here, displacement, angular displacement is in radians, angular velocity, radians per second. All the language is in terms of angle. If you ever want to pop from one side to the other, the extra ingredient you're going to need is the radius of circle that this particular object is making, a particular point on the object. So then, obviously, the one thing we need to address further is what about if the object is spinning, but also spinning faster or slower, right? Spinning, slowing down or speeding up. So that's where we get to the final quantity, angular acceleration. This is the Greek letter alpha, which is basically the Greek equivalent of A. Okay. So angular acceleration is kind of the bizarro version of regular acceleration or linear acceleration. It's defined exactly how you might think it is. It's how the angular velocity changes with time. We can compare it to how regular or linear acceleration was defined back in homework number 2. It's the exact same deal. This stuff is so similar, it's almost like we're making a change of variables. with the understanding that instead of talking in meters for everything, we're talking now in terms of angle. So this was, of course, measured in meters per second, or meters per second squared to be condensed. Now just switch out the meters for radians. This is measured in radians per second, or to be concise, radians per second squared. All the same stuff. Now remember that, of course, acceleration, we've done a lot with that since we introduced it. We talked not only about being able to speed up or slow down, we talked about the fact that you can use acceleration to change direction. So things like centripetal acceleration, right? But let me remind you that when we're moving in a circle, we said that there was a highly analogous behavior to one dimension, right? Because in a circle, you can only go one way or the other way, plus or minus, counterclockwise or clockwise. So let's bring back our one-dimensional stuff. Remember, we said when the velocity and acceleration are in the same direction, what happens?
Speed up.
Speed up. When they're in opposite directions, you slow down. And of course, even the more simpler possibility, if the acceleration is 0, the velocity does what? It's constant speed, right? Okay, so we know that stuff. That stuff's old hat. Hopefully you absorbed it well at the beginning. So now we can use those ideas. Let's just apply it over here. Omega and alpha. Those are the angular velocity and acceleration. If they're in the same direction, what do you think happens? You speed up. If they're in opposite directions, you slow down. And if the angular acceleration is 0, what happens with the angular velocity? Thank you. I just heard birds there for a second. Okay. So, all the same stuff. So, really, it's all being very strangely familiar. There are a little bit of catches, though. And let me show you what those are. I guess I'm going to have to clear a little bit of space here on the top, because I want to save this over here. So let me take a look at a circle. And I'm going to be going in a circle at a constant rate, constant speed. So I might draw my velocity vector like this, then like this. I might call this V initial, this V final. So I guess first of all, I'm going counterclockwise, right? So if I'm talking about the angular variables, what is my direction of motion? Positive, right? Counterclockwise is plus. That's counterclockwise. What's my angular acceleration if I'm just going at the same angular speed the whole time?
0.
0. This is constant, right? It's constant in size and direction. So everything about the angular velocity is constant. I'm sweeping out the same amount of angle per time, and I'm doing that in a continuous counterclockwise fashion, which for angular stuff, that is a constant direction, counterclockwise. Now, let's switch over to the linear side, the old stuff. My velocity. Okay, is the size of my velocity, v, is that constant? Is this the same, should this be the same size as this?
Yes.
Yeah, but what about the direction? No, that's not the same direction. So, do I need acceleration here to make that change in direction? things don't change in direction on their own. In fact, we have a very special name for the type of acceleration it takes to just change the direction of the velocity.
Centripetal.
Centripetal. So the acceleration is not zero. So we run into a little bit of an issue here, because if these two guys are going to be kind of the cousins, one of them is zero and the other one's not. So they cannot be, I cannot, for instance, try to say that A equals R alpha. That obviously doesn't work. So this is where I can remind you about something that we did bring up when we were introducing circular motion, and we promptly threw it away for later. Later is now. So what we said was that when you're going in a circle, there are two types of acceleration, or I should say two components to the acceleration, that have different jobs. A tan is the component that we threw away, and a centripetal, of course, is the component that we focused on at the time. A centripetal changes direction. That's what keeps the motion in a circle rather than something else. We learned that going in a circle is a privilege and not a right. Okay? So that much is going to have to be the case. You're going to need a centripetal acceleration. Okay? So the centripetal acceleration is necessary to hold us in a turn. Now, why didn't we have anything like that on the angular side? Well, the angular side, its number one assumption is that we're going in a circle. It doesn't ask what it takes to go in a circle. It just says, let us start with the premise that we're going in a circle. Can we describe stuff? Okay? And so the centripetal acceleration is completely does not have any analogy in the new rotational world, the new angular world. Acentripetal is what it costs you to go in a circle, but in the angular world, we assume we're already doing that. Okay? So if I'm going to write my linear angular box here, and I'm going to leave a third line there, completely outside of it is acentripetal. That's the unsung hero that makes sure that I stay in a circle in the first place. So that was our focus earlier on when we were doing homework 6. But we also threw out a tan at the time. This is what changed the speed. This is for speed control. Remember, this is a component of your acceleration that could be with the velocity or against the velocity. And it was very analogous to our one-dimensional behavior, right? It can either be with the velocity to speed you up, or opposite your velocity to slow you down. What we really meant here in a circle is that this is a tan. Okay? A tan can point with you or against you. This and this are buddies. Okay? They go together. They either are both acting with their respective velocities to speed you up, they're acting against their respective velocities to slow you down, or they're zero, in which case your speed is not changing. Okay? You can either talk about that speed change in terms of linear variables or in terms of angular variables, but these two guys are the cousins. So I'm going to add here, not that I've proven this rigorously or anything, but these two are the analogous quantities. They're both for speed control. One is in the linear world, one is in the angular world. Alpha talks in radians per second squared. It's talking about how your speed is changing in terms of angle. And A tan is tasked with that same description, but in meters per second squared. Okay? So we found the rotational and linear analogs. I should point out that, of course, A tan and A centripetal are really part of the same acceleration, right? You don't have two accelerations. You have one acceleration which has two different jobs to do, and we, to get it around our heads, split up that job into two components, right? We have one component of the acceleration that controls the speed of the object, and another component which just deflects the direction and continues to allow it to be on a circle instead of having it fly away. So we will occasionally need to remember to assemble those components, okay? Because there really is only one acceleration. One component has a rotational analog and the other one does not, okay? So with that in mind, let's take a look at something which is going in a circle, but not something that simple. Something that is not going at constant speed. So in this case, alpha was 0 and A tan was 0. Those are, of course, analogous. But let's take a look where that's not the case. Okay? Are there any questions before I clear a little bit of room on the right side of the board? Yeah?
So if we know about A tan, can we calculate eccentric orbits? I mean, does that help?
Yeah, that'll certainly, I mean, these ideas, A tan and A centripetal, are still relevant for elliptical orbits, but elliptical orbits are going to be more complicated, so we're not going to look at them in this class. So for us, we generally look, the only kind of closed form thing we look at is a circular orbit. So let's take a look at something which is going in a circle but speeding up. So it might look like this. Here's V initial, and here's V final, like this. So notice that I've kept it going in a circle, but I've drawn the final velocity vector much longer to indicate it's speeding up. Okay? So this is clearly speeding up. So let's say what we can write down about this situation. First of all, what is the direction of the angular velocity? Positive, counterclockwise, right? We're proceeding in the counterclockwise fashion. We're speeding up, so what does that mean about the angular acceleration sign? Same sign or opposite? Same. You're going the same direction. Or if those point in the same direction, it's reinforcing what the angular velocity already has going on, right? They're the same direction because you're speeding up. All right? So, let's look on the linear side. Do you have an A tan? Is there a component of acceleration that is tangential to the circle? Yeah. If you have alpha, you have A tan. Okay? So these are just two different ways to talk about how the speeding up is occurring. Does A tan point with the velocity or against the velocity? With the velocity, right? Same direction. So V and A tan have to be in the same direction. So now we have that there is going to be a part of the acceleration that is with the motion, A tan, like this. So those are just two different ways to talk about the speeding up, right? You can talk about the speeding up in terms of alpha, which is radians centric, or A tan, which is in terms of meters per second squared. But, of course, on the linear side, that's not the end of the story, because you're not just speeding up along a straight line. You're speeding up in a circle. So you need that other component of acceleration just to hold you in the turn. So we might draw that in, A centripetal, hold you in the turn. And so, those are just two components of what is actually the overall acceleration. The overall acceleration appears to have an inward component and a forward component, so the acceleration overall looks like this. Remember that there really isn't two accelerations. There's one acceleration which has pieces that point both with the motion to make you go faster, and inward to help you hold the turn. So, what we might ask is, what is the angle between the velocity and actual acceleration, right? So you can see here that the angle between the velocity and acceleration is less than 90 degrees, right? Because the acceleration is both inward and forward. Anytime you're speeding up, that will be the case. When you're speeding up going in a circle, the angle between your velocity and acceleration is less than 90 degrees because the acceleration has to be, yes, inward to hold the turn, but also forward to help you when you're going faster. So let's go through all the cases, okay? I guess my velocity was in black, so I'll have this black pen sticking out of my chest, okay? Wherever I go, it of course just says which way am I going, right? Then I'll have my red, my acceleration will be, of course, what helps the velocity evolve. If I want to go faster, then it's going to need to point like this. It's inward and forward, right? So it's inward and forward. It's both with the velocity, but also holding me in. So it's like that, less than 90 degrees. Now, if I want to slow down, it's going to look like this, right? Because then the acceleration has to be inward and backward, right? So inward to help me hold the turn, but also against the motion to slow me down. So if you're going in a circle but slowing down, the angle is greater than 90 degrees. Does that make sense? So I can write that down here. This is if you're speeding up. If you're slowing down, the angle between your velocity and overall acceleration is more than 90 degrees because the acceleration has to be inward, yes, but also backward against your motion. What's the only time where the velocity and acceleration will happen to make exactly 90-degree angle? Any ideas?
It's not accelerating.
Well, it's accelerating because it's going in a circle.
Speeding up.
It's not changing speed, that's right. So the acceleration is inward to hold the turn, but it's not forward or backward. It's not helping you or hurting you in your speed. So only then will the acceleration as a whole be synonymous with the centripetal because the tangential is turned off. It's not helping you or hurting you, right? So at constant speed, that is when the velocity and acceleration are exactly perpendicular because the acceleration is inward only. Basically, the acceleration is synonymous with the centripetal because the tangential is turned off. This may give you a little bit of insight as to why we call the acceleration needed to hold a turn centripetal. It's because the centripetal is just one part or one component of what may be a larger acceleration. An acceleration generally can have a part that holds the turn, which we call the centripetal part, but it may also have a tangential part, which is going to control the speed. Okay? Okay. Are there any questions on that? Okay, and I guess I should mention, remember the Newton's second law, F net equals ma, so F net is going to, of course, always point in the same direction as the acceleration. So if there is an overall acceleration, that's because the net force points that way. So for those of you that might be into car racing, maybe you just saw Fast and Furious 7, okay? We can talk about how this all applies to cornering. So if we take a car that has a certain velocity, if you are going at some insanely fast speed, the thing that limits how fast you can go is, of course, the friction from the ground, right? There's only so much friction to be had from the ground, and if you ask for more, you're going to crash, right? So we have something in car racing called the circle of friction, which is basically the amount of maximum force you can get from the ground is a fixed number. You can choose to devote that net force and acceleration all in the forward direction, but the problem is you haven't left anything for turning, right? So what we can imagine is if there's a certain kind of maximum force and maximum acceleration you can get from the ground, we can imagine it as kind of a sweeping around like this. We can decide how this total acceleration that we can get is a fixed number, right? But we can choose which direction we apply it. Okay? So we can choose to apply it all forward, but we're not going to make a turn, right? We can choose to go into cornering. So this is the cornering. We're applying our limited resources all centripetally, but guess what? We can't speed up then. We've used all of our resources into that, right? So we can use it all into speed control. We can use it all into cornering. But if you use some for one, you can't have it for the other, right? So for instance, if you're trying to corner, but also pass somebody else, that would be like this, right? This, you have a component of acceleration centripetally, but you've chosen to take away from cornering and apply it to tangential, right? You want to pass somebody else. So you're going to try to exert a tangential component, right? You want to make your velocity faster. But guess what? If you're trying to pass somebody, and so you're using some of your resources tangentially, you have to give on the cornering. And so you may fly out attempting to do that. Now, that may be okay. Maybe you are going to plan to fly out of your circle. Where are you going to fly? Hopefully not crash. Hopefully just go into a larger circle, because look at a centripetal. The formula v squared over r, if you go to a larger circle, then you don't need as much centripetal acceleration. That's why you usually pass on the outside, right? If you're going to devote some resources to passing somebody else, a tan, you're not going to have as much a centripetal. So you want to be planning for that, right? You want to be planning for the fact that you are going to fly out of your circle, and you want to plan to do it, fly into a bigger circle, not to crash into a tree, right? So this is called the circle of friction. It has a lot of implications for any time where you're trying to go in a circle, change your speed, and you have a limited amount of resources because you're going so fast that the acceleration and net force you can get from the ground only goes up to a certain amount. Okay? Are there any questions on that? Okay. So you can actually find information about this, I think in even some owner's manuals for your car, you can find information about this. Okay? So the last order of business we need to do is to develop the constant angular acceleration equations. Okay? So let's do that. Now, this is going to be a relatively straightforward proposition because everything is so highly analogous. In fact, all I'm going to do is this. If I have my plus x-axis, my good old classic one-dimensional situation, I might have, here's my initial point, here's my final point. I might talk about things like, what's my displacement, right? My displacement like that. I might talk about what is my initial velocity at the beginning, and what's my final velocity at the end. I might talk about whatever acceleration is applied between there, and of course the time taken, right? All this stuff that we did in homework number 2. For instance, we might take one of our good old classic equations, like this guy. It's been our old friend since the second homework. And all I'm going to do is I'm going to take this, and I'm going to imagine that my axis can be bent into a circle. So everything that I just talked about, initial and final, all of that stuff can be mapped onto the circle. Now remember, there's an unsung hero here. You can't turn a linear motion into a circle without having something to hold it. So a centripetal is kind of like what allows that axis to be folded like that. But now, everything that's along this line is now going to be tangential to the circle, right? So this is, for instance, my V initial, right? My V final, things like that. Now, because I'm moving on a circle, all of the stuff that I was previously doing in meters per second can also be described in terms of angle, right? So let me put in my equations. My distance covered can also be talked about in terms of angle. I just put in r times delta theta. It's the relationship I just used. My V initial is going to be r times omega initial. My acceleration here, this is of course acceleration along the line. So now that's just a tan, that's r alpha. So everything got replaced with its angular counterpart. Well, check this out. The r cancels. So what I get back, and this is pretty handy, I get back the exact same equation with all of the variables replaced by their rotational versions. So my constant acceleration equations become my constant angular acceleration equations. The only thing I have to do is replace everything with its rotational counterpart. Okay? Every single one of those will work the same. So my constant angular acceleration equations, how do you get them? Replace delta x with delta theta, v with omega, and a with alpha. They're exactly the same. That's why they're not even on the equation sheet, because it just blows too much space. Just take the ones that are already there, replace everything with its rotational analog. You have a new set of 5 equations that can be applied, same as the old ones. So what I'll do next lecture is I'll do an example to kind of tie this all together. So I'll do an example on Monday, and that will finish off homework 8.